Today's presenter is Martin Baumann, Business Development Manager, Hot Runners at Husky Injection Molding Systems, and has been with the company for over 15 years. I'm Josh Durrell, Director of Business Development for IDES. I'll now turn over the presentation to Martin Baumann.
Good afternoon, everybody. Thank you very much for participating for the next 45 minutes to 60 minutes, and we appreciate you dialing in. We will be talking about color change this afternoon, and one thing I would like to point out right in the beginning, if you want to become a master of color change, it's not just driven by one issue. A lot of people come to us saying, I have slow color change, it must be the hot runner. But what I would like to talk about this afternoon a little bit is that it's really a system. There's actually many influencing factors that drive color change, and we would like to talk about them in the next 45 minutes. So we'll start off with understanding colorants and pigments. Like, depending on what kind of color you actually use, it does make a difference. It makes sometimes differences from one color to another color within the same family. We'll talk about polymer flow and color change, why the reason plastics are sometimes difficult to color change. We'll talk about equipment design considerations, the impact of melt viscosity and homogeneity, and then at the end of the presentation we will talk about planning for effective color change, and we also have some recommendations that you can, of course, and actually try in your plans in regards to specific process setups for fast color change. Before I start, I would like to reiterate again, it's really a systems approach, and the more you understand about the overall, we believe actually the better chance you have to actually save some dollars and become a master of color change. So we'll start with the pigments. In principle, there's actually two large families of pigments. There's pigments that are insoluble. It's basically like, think about like sugar mixed into a plastic resin or in a matrix, so it's really small particles basically. Could be in powder form. Very often, of course, they already come as master batches, but it's basically like a bunch of molecules together. On the other hand, there's dyes, and they're really liquids, very similar to water, of course, and often water-based. And they basically break down into almost individual molecules and then attach themselves to the molecule chains of the polymer matrix. Our own estimates are probably 80 to 90% of what's used in the industry is actually like insoluble pigments, and we will talk about those a little bit more in detail. So of those, that family breaks down actually into organics and minerals. And in that family we have, on the organic side, we pretty much have only non-effect particles. So minerals can actually have effect or non-effect particles. And effect particles are basically what you would see like in a metallic kind of color, where you get these glittering effects. That would be actually a so-called effect colorant. And they actually present their own challenges sometimes when it comes in mixing them properly into the polymer matrix. So how do different pigments work and what do they do? And there's also, I think, an important thing that needs to be considered is actually the size of the pigments. They play a key role in how well we can actually mix them within the polymer matrix, and what are some of the challenges later on when it comes actually to color change. So the organic and inorganic pigments, they're in the range of 0.01 micrometer to about 1 micrometer. And they're sort of touching on what typically would be a filler like calcium carbonate or graphite. They're roughly in that same neighborhood. And then there's the platelet-structured pigments. They're a lot larger, like very significantly. They're in the range of 10 micrometers to 100 micrometers, and they actually have a real structure. Almost like, think about it as a small rectangular plate, for example. And because of that, they can act almost as mirrors. So the inorganic and organic pigments, they react mostly as absorption pigments. They basically swallow some of the light and reflect only portions of it back, and that's what creates then the color for those pigments. On the other hand, the platelet structure pigments, they're reflection pigments, and they can react either as straight mirrors, reflecting basically the light back as it comes in, or as prisms, reflecting the light actually in different colors as it comes back, and those would be then actually creating some of these sparkling effects that you have seen, especially when the sparkles appear in different colors. So in regards to size on the organic, for the organic pigments, we have sizes between 0.01 and 0.1 micrometers, so very small. And in order to get, let's say, if we want to mix 1% of colorant into a polymer matrix, as you can imagine, we actually need a lot more, sort of, just from a pigment count point of view, we need a lot more on the organic side versus on the mineral side. So the specific surface area for organic pigments on the smaller side is actually a lot larger compared to the minerals. And that actually has an impact in regards to mixing and what kind of effort you have to take to really mix them actually well into the polymer matrix. So how do they work? And the organic pigments, the small ones, very well distributed, that's the assumption within the polymer matrix. As light actually comes in, they let very little light through because we got lots of these little elements basically distributed in the polymer matrix. So from an opacity point of view, if you're mixing the same amount of pigments into a polymer matrix, the minerals would be letting a lot more light through because they're larger elements, and at the same time they're spaced further apart. So those would be the colors that you typically on a plastic part you can actually sort of look through and have an opacity to it. Very similar, same thing actually happens in regards to color strength. The organic pigments, well distributed, will be reflecting a lot more light back, and therefore actually have stronger colors, the dark ones, in that respect. And as we will see later on, also the ones that are a little bit more difficult to color change, of course. The minerals on the other side, because there's less elements for light to be reflected back, will be not as strong when it comes to color strength for the same amount of pigment. Now, in regards to dispersibility, there's an important thing. The smaller elements are a lot more difficult to mix. We got lots of these ones, and they have an affinity to each other, so they actually like to stick together. Versus the larger elements on the mineral side, they're a lot more easier to mix. And I think a good comparison is actually, some of you may have been cooking at home, trying to make a buttery sauce. I'm actually not that lucky with that kind of stuff, I will admit. But think about mixing flour into a sauce hollandaise. And you have to actually use your whisker quite strenuously to actually get that properly done. Versus mixing chocolate chip cookies into a chocolate chip muffin is actually a lot easier. And part of that is actually because of the size of the pigments. The ones on the left, the organic ones, they're easily actually sort of clumping together. And if you do not mix them properly, you get concentrations, you get problems with your color distribution in the part. You can get, in a worst case scenario, you can get streaks. Or from a color change point of view, if it's not properly mixed in, these concentrates then actually start to leak out. We're losing pigment by pigment, one after the other, and it actually keeps showing up in the part. So minerals, a lot easier to mix, a lot easier to color change too in that respect. So we will be doing our first survey. We have throughout the presentation actually 3 quick surveys just to support the presentation. So how often is color change discussed at production meetings within your facility? Just have a quick click on that, and we will actually get the results immediately back. So majority of you, actually 38%, and even sometimes 35%, so vast majority of you actually discuss color change in production meetings. And I think it's pretty clear why, because in a way, color change typically produces waste. And this is one of the things, of course, doing it more effectively, you reduce costs and reduce waste. But before we go into the details of color change, I want to talk a little bit more about the physics of polymer flow. And I think most of you know we have a plastic laminar flow, but I just want to reiterate it again. Within the resins, we don't have any turbulences. So we're actually not mixing resin or anything like this after it enters screw and barrel and later on in the hot runner melt channels. We have laminar flow. And that laminar flow actually has some consequences when it comes to color change. So in regards to our shear and velocity profile, if this is a melt channel and we have plastic going through here, in theory we have actually zero velocity on the inside wall of that melt channel. And by having zero velocity, that actually also means we have basically no movement. In reality, there's a little bit, but just from a calculation point of view, this is what's happening. At the same time, we actually have very close to the wall, we have the largest shear rate. Shear rate, by the way, is a good thing for color change. It's almost like sort of rubbing your hands against each other, create shear, moves molecules, so to speak. And that helps actually clean out that area. One of the consequences of this fountain flow principle is then, if you look at the layer of material, in this case this is demonstrating a gate detail. This would be a hot tip gate. This is the cold gate insert. This would be the cavity steel. And we have this little layer of material, and as we're flowing due to laminar flow, whatever remaining material is, if we have first injected red material and then want to follow up with a yellow material, we would be seeing that material actually ending up on the surface. So most of you probably know if you do a color change, the actual color on the part changes usually over very quickly. It doesn't take only a couple of shots if you change even from a black to yellow, but on the surface, sometimes for a very long time, you keep seeing actually the old color. And the reason why that is because of the laminar flow of the polymer. This is actually a good example. We actually pulled one of the melt channel after it was cooled down from one of the hot runners. And as you can see, actually, the theory is actually supported by reality. And what we're having here is an outside layer in that melt channel of about 0.3 millimeters. And this is all due because we were able to push the inside of the material. 98% is already white, but we have this relative persistent layer towards the inside of the melt channel. This is actually very difficult to remove because we have zero velocity in that area. So coming back to a system consideration overall. So while we will be talking a little bit more about hot runners and melt flow, I want to stress the point again. You can do all the right things on your hot runner and in your screw and barrel, but very often what's overlooked is actually what's happening even up front with that. So I just want to draw your attention to also to make sure that resin conveying and color dosing can actually be flaws in the system that actually slow down your color change if you don't properly clean it out, if you actually created, for whatever reason, hang-up spots in your piping, if you don't clean the old color properly from your hopper and keep running, start purging, and then you have certain corners or hang-ups because the material wasn't dried properly or something, that material will keep bleeding into a screw and barrel, and of course eventually will end up in your part. In regards to screw and barrel, very important, especially if you work with the smaller or organic-sized pigments, good mixing capability. We do not want to have color concentrations that show up later on the part and slow down color change. We don't want to have bridging in the feed zones, and very important too is sometimes you have to change nozzles and other things. Make sure there's no mismatches. And of course, if you use a check valve, make sure there's no hang-up spots, and the check valve is actually optimized for color change, especially if you do very frequent color changes. So look at this whole thing basically as a system, not just as a hot runner issue from that perspective. In your hot runner itself, what we're looking for as an overview, we want to reduce the volume of the melt channels. The less material we have to replace, the better. We want to have no mismatches. We want to have no hang-up spots. And one thing, and we'll talk a little bit more about that a couple of slides down, a uniform temperature profile is actually also very important for an optimized color change. And if possible, you have some mixing capabilities in the hot runner itself for further color and distribution. So what are some of the best design practices for the hot runners, or things to look out for or ask your hot runner supplier when it comes to color change? For example, like in manifold bushings, make sure that they got nice, round, smooth corners, that there's no gap between the bushing or the plug and the manifold, because material actually can creep into these gaps. So fit very important. Fit of the stem, very important. The manifold itself, any kind of manifold channel mismatches should be avoided. The channel layout itself should be optimized for color change, and a good balance between pressure drop and shear rate, and thermal uniformity, of course. The sprue bushing should be the same size from an orifice point of view as your machine nozzle, and I will show you the example in just a second why that actually matters. The plugs need to be blended properly, and in the tip area, right in the front, we're trying to minimize how much material is actually sitting against the cold steel of the gate inserts, because that material settles down there, and if we're changing colors, there's a potential for that material to keep bleeding actually into the part and ending up on the surface of your plastic part. So the first thing, very often overlooked, of course, everybody changes molds from one machine to the next. But one thing that I would like to point out is that it's often forgotten. It's very important that you actually match the machine nozzle orifice with the sprue bushing orifice. Often overlooked because everybody is in hectic and has no time. But a mismatch of 1 or 2 millimeters won't actually hurt your injection molding capabilities, but from a color change point of view, what you just created is basically a dead spot of the old material sitting there, not moving, and then keep actually like bleeding into the melt stream and prolonging your color change. So always a good thing to check. An optimized version, of course, is like make sure that the machine nozzle orifice and the sprue bushing orifice actually match with each other. A similar problem could be if you have like worn out surfaces and dead spots in this area, that will actually cause problems too. Now in regards to melt channel sizing, I have a brief video that I would like to share with you, and that explains a little bit, we will run it twice, what we need to balance in regards to pressure drop and shear rate. In principle, a higher shear rate is good for color change, but what's very important, we need to make sure we don't overdo it, because otherwise the pressure drop will increase. So what we're seeing here is sort of a melt channel of 8 millimeters, and now we're making it smaller. As you can see, the shear rate and the pressure drop will actually go up. Residence time will go down. If we do the reverse, if we're making the channel larger, I will rerun it once more. So shear rate, as we go smaller, goes up, pressure drop goes up, residence time is down. This is all good things for color change. As we go bigger, residence time will go up, shear rate actually will go down, and pressure drop will go down. Now what we're trying when we actually optimize a system, we're trying to balance those. Because of course we still want to be able to fill the actual plastic part at the end of the day, and we don't want to have situations where you're pressure limited to fill the part. But if you come to us, for example, with a color change application and frequent, we will pay a little bit more attention to shear rate versus the pressure drop within the limits of the machine, given, of course. Now we'll move on to melt viscosity and the effect on color change. So first, a not so good condition. If we're trying to purge out a high viscosity material, a tough material, with a lower viscosity material, an easy flow, you see actually what's happening. The material on the inside just doesn't have sort of the strength to push out the higher viscosity material. It's actually one of the reasons why in plastics we're able to inject water and air into the melt stream for like gas injection, for example, what would have very low viscosity, of course, relative to the resin. Because of the laminar flow principle, we can push that material through the center core. From a color change point of view, of course, that is not a good situation. A better situation would be if you want to do quick color changes, if we have the high viscosity resin on the inside and really scraping those walls with the lower viscosity resin. Now, in many cases, of course, like color change is actually done with exactly the same resin, so you don't really play that much with different melt flow indexes if you want to do color change. But there's one way how we can actually influence that too, and that is with temperature. Temperature has a significant impact on melt viscosity. So this is again the example that is not optimized for color change. If we have let's say a manifold or melt channel temperature on the outside of 350 degrees Fahrenheit, and we're pushing through a melt coming from the barrel with 450, that means actually we have on the inside lower viscosity resin drying to push out higher viscosity resin. That doesn't work that well, assuming these were the same resins. So a better situation would be if we actually increase the melt channel temperature, therefore actually changing the viscosity on the resin, lowering it, and pushing from the inside a resin, the same one, at a lower temperature. And by lowering the temperature, of course, we're changing the viscosity and making it a tougher material to push, and that actually helps for color change. That's one way of optimizing color change. So let me move on to thermal uniformity and why that actually matters, and it's of course closely related to the temperatures. This would be a manifold that wouldn't be necessarily optimized. It has a very hot area right around the entrance of the resin, and then a cooler area on the other side. And what we actually pulled from this manifold is also the plug, and you can see already a little bit. I have a detail in a second. This is lighter. That means like if we change color from black to white, we can see the white already coming through in the hotter area, versus there's more black on this side. So this is the blown up version of this. So cold area in the melt channel, section AA, you can see clearly a lot more boundary layer. So this is the same injection condition. This is the same hot runner, just two different sections in that hot runner base at two different temperatures. And then on the other hand, you see the BB section view, significantly reduced outside layer. Now you can imagine the effect on color change of this one will take a lot longer to clean out section AA versus cleaning out section BB. An optimized manifold for color change is actually a hot runner that has a uniform temperature profile. Hotter is actually not bad, but the best situation, of course, is a uniform temperature profile where we then actually can, as operators, play with the temperatures as we need it. We don't want to go too hot either, of course, because eventually we start burning the material, and that's not a desirable outcome either. The other portion, the hot runner, that's very important from a color change point of view is actually the interface or the gate detail between the hot nozzle and the cavity itself. You see here a blown up version of just that detail in the front. And pretty much with every hot runner system, you need to have some kind of gate bubble in the front. This acts as an insulator, protecting basically the hot tip on the inside from the cold steel. If you would be touching this tip right to steel, it would be losing too much heat, and the operating window of a hot runner system would be vastly reduced. So we need that insulating layer, but if we shoot first, for example, with a red material and then want to follow up with a yellow, you can imagine that red material sitting in this area will be sitting there for a long time and keep actually bleeding into the cavity. A better way of doing this is using a so-called insulator. It's typically a thermoset material, and it gets basically put in a space where normally the resin would be. And by doing so, we're actually reducing significantly. You can see there's a big difference between this gate bubble and this gate bubble. And that's a lot easier to flush out when we actually follow up with a new color, for example, yellow or something else. So very important for an optimized color change, reduced gate bubble is a preferred option. And why do we want to flush out that bubble? This is just the example again of just a little bit more blown up. Because of the laminar flow of the resin, while we have pretty much changed the maturity of the resin already over, the former red material sort of clings to the outer surface, and therefore, from a visible point of view, when we do color changes, we always treat the streaks on the top of the surface of the part, and of course, then these parts become scrap because that's not something that you as a customer can sell to your customers. Tip insulators have proven to make a big difference. Like in every case, it's a little bit different, but we have seen up to 75% reduction in using an insulator using the same resin and similar colors. So a pretty significant difference here. The other thing I would like to talk about is as sort of a technical solution to color change is what Husky offers is a mixing tip. We call it the UltraFlow. And what it does, it takes the resin right before it enters into the cavity and actually mixes it. It doesn't create any turbulent flow. We established that you can't do that with, because of the Reynolds numbers, we can't do that with plastics. But what we can do is if we can create crossing melt streams, that's actually what does mix plastics. And that's actually what the tip does. And I'll show you another quick animation that actually demonstrates this, how this actually works. And I just want to remind you, this is right before the melt enters into the cavity. So we're demonstrating here color change, so the yellow color is trying to push the blue out. And what we're doing here, we're forcing the material first into a spiral, but then at the same time, very important, we're opening a gap here and we get actually flow along the torpedo too. Now that's very important because we have to have both. If you would only have the spiral, that wouldn't be enough because we cannot create turbulent flow with plastics. But if we create crossing melt streams, one flow is still going this way and the other one going along the torpedo, we actually create mixing within a hot runner system, or in this case within a nozzle tip. So what does that do? I show you an example here. So this is again a tip pulled with frozen material at the end. You can still see here this was a change from yellow to black. Most of the yellow is already gone, but you see on the boundary layer here we're still having some yellow material actually left over at the entrance of the tip. Now as we exit the tip on the front, you can see actually that layer is gone. It's basically mixed under. It's within the black material now. It's hidden. It's within the matrix. And that's one way actually of how you can actually speed color change. You don't really eliminate it, but what you basically do, you make it disappear for the eye. This is just a comparison that shows this just once more, a little bit more in detail. We're changing color from black to yellow here. On the top is the UltraFlow tip. On the bottom would be a standard tip that typically splits the melt either 2 ways, 3 ways, or sometimes 1 way. But most hot tip systems actually have a split in the front. And you can see we're changing even after 5 shots. Pretty much all of the black is gone. Most of it is yellow. But on the surface, we do see some of the black material. With an UltraFlow tip, after shot 60, it's all mixed under, and you actually can't see it anymore. With a standard tip, because we're concentrating the color, because we're splitting the melt in these 3 areas, it's a lot harder to disappear, and you can see after shot 60, there's still a slight trace of that colorant in the part. And that's why the UltraFlow tip actually speeds up color change. I would also like to point out actually one of the other things that the UltraFlow, or the mixing function of the UltraFlow tip does, it homogenizes the melt right before it enters into the cavity, and that in some cases actually has proven to enhance the mechanical properties. More homogeneous melt, less flow lines in that respect, better mechanical properties of the plastic part. I have an example for you here. For a 72-drop hot tip hot runner, 3 grams, 12 melt polypropylene. And again, depending on the resins, depending on the colorants being used, every situation is a little bit different. But in this case, we have been able to achieve 15-minute color changes on a high cavitation hot runner system. So at this point, I would like to actually introduce one more survey, if you don't mind. So how many color changes are performed at your facility per week? Just think a little bit about this, how much is done. I know some molds actually run almost every day, others don't, but just give us a good average, and we will work with those numbers. So very few people, 22%, do actually less than 5 color changes per week. Pretty significant number actually do between 6 and 50. That's actually the majority. So quite a few color changes per week, and some people actually do 50 and more color changes per week. Now think about what a color change really is. It's sort of an interruption of the process and of your production flow, and in most cases these parts actually have to be thrown away. So I just want to give you an example what it means actually, and I just used the UltraFlow here, but what it could mean, and we're more than happy to run actually numbers for you on your specific applications if you want to contact us. It's very easy to do. But I prepared an example here of a 72 cavity, 3 gram part weights, 5 color changes per week, and assuming the mold runs 45 weeks per year, resin costs of about $2.8 per kilogram. And then just as a reference, a standard color change, 260 shots, and UltraFlow, or by other means achieved enhanced color change, 70 shots. Now you look actually what that does to you in regards to resin savings and dollar savings, the numbers become pretty quick, pretty actually significant. A standard tip, for example, in this case, we used up over the year 12,000 kilograms just for color change. All scrap material, nothing you can do with that. With an UltraFlow tip, about 3,000 kilograms. Now in regards to dollars, pretty significant savings. $36,000 versus $10,000. So we're talking about a savings from a improved or more effective color change versus a not so effective color change of 73%. That's pretty significant. This was, by the way, this was just for one tool. So if you run multiples of those, or if you change the numbers from 5 color changes to 10 color changes per week, you can imagine what the impact is. Another topic that I would like to talk about briefly is melt mixing and color dispersion. I think it's very important actually that from a screw and barrel point of view, because otherwise you start wasting actually either colorant or in this case what happened, because the melt wasn't properly mixed, you can see actually in this area of the part we have color concentration. Remember from the beginning I said, especially if you work with the smaller particles, with the organics, more likely to happen in that respect. And often what processes do, they overcompensate for this by adding more colorant, what is of course a more expensive way of doing it. One solution actually what helps, two actually, like one of course have a proper mixing screw and barrel, and the other one is actually with an ultra mixing tip through a hot runner solution, we can actually help to disperse the material right before it enters into the cavity. The other thing, especially with pearlescent, remember I mentioned in the beginning, some of these effect colorants, they tend to come in larger chunks, in larger pieces, and especially the rectangular ones that actually have a real shape to the pigments, they have a tendency whenever they get split in a melt stream or not properly prepared, they pretty quickly concentrate and then give off actually different colors. And what we can do here too is by dispersing it, for example, with an UltraFlow or doing it properly in the screw and barrel, we can achieve better results and also faster color change by properly mixing the colorant into the polymer matrix. Very important. So I would like to move on now to a couple of practical aspects. And first, color change planning. And I understand not everybody can always plan ahead of time which colors are coming up. We all have crazy customers that don't give us good forecasts. But trying actually sometimes helps too, and then sometimes you do actually know what's coming up in regards to colors, and it does make a difference. And I just give you a quick demonstration here in regards to the impact of a not optimized color change versus potentially optimized. So in this case, we're changing colors between the yellow and the blue and the green and the blue and the darker ones. A total, let's say this would all have happened in a given day, we would need 600 shots, or for this 32 drop mold with a 3 gram part, 57.6 kilograms of material in a given day. An optimized sequence, just looking at the colors, would actually be going from the light blue to the yellow, from the yellow to the green, then to the dark blue, and then to the light blue. And just by changing the sequence within that given day of these parts, we're actually using 400 shots or 38.4 kilograms, what is actually a 33% reduction in resin usage. And again, depending on the part weight and everything else, these numbers change, but I think it gives you a pretty good idea how important actually planning ahead is when it comes to color changes and scrap reduction. Now, one point I would like to make, there's some colorants and actually some colors within different colorants families that just seem to be actually more difficult to change over than others. And blue is a good example. Some of the reds are doing this, and sometimes color change can actually take 700 shots or 1,000 shots, no matter what you have tried, so to speak. So one way of getting around this is actually using purge compounds. We don't recommend purge compounds for every color change. We don't think it's necessary. But from a planning process, if you know which colors take longer, and if you have cases where it takes really long, like 700, 800 shots to go from one color to the next, a purge compound is actually a very good alternative, or a very good sort of, from a process point of view, that you can introduce in your factory. And again, depending on the application, we have seen up to 80% reduction by using a purge compound when it comes actually to color changeovers. And most of the purge compounds available in the market actually can be used within hot runner systems. Ask your hot runner system supplier what he recommends. We recommend UltraPurge. And by the way, you can buy it from Husky through our Buffalo spare parts facility. But this might be something that you may want to actually consider in the future when it comes to color changes. But usually not required for everyone, especially if you go from a light to a dark color. Typically, you don't have to introduce a purge compound. This leads us actually to our last survey. I would like to do one more, and the question is coming up. Do you have a written color change procedure in your facility? Thank you very much. So I'm actually not surprised. I have to say, unfortunately, most of our customers don't have a written color change procedure at their facility. So 56% of you actually don't have one. I highly recommend establishing one, because it actually does make a difference. And you've seen in the examples that I demonstrated before, it has a real impact on the dollars. And it's just not one thing that needs to be changed, but this definitely will help. So let me actually walk you through what we recommend in regards to color change setup. And I start first with temperature setup. And this really comes back to what we learned earlier in regards to viscosity management. So from a best practice point of view, what we want to have is actually the lowest temperature and therefore the lowest viscosity resin on the machine nozzle. So we want to push that tough resin inside those hot runner melt channels. We want to have slightly elevated temperatures on the hot runner manifold, and we want to have the highest temperatures on the hot runner nozzle. And the reason why on the hot runner nozzle, because we need to remelt portions of that gate bubble right in the front where it touches actually the hot steel. So in general terms, that's our recommendation when it comes actually to temperature management for color change. And of course, something like this then can become part of your written color change procedure. So how do you actually do a color change procedure? So the first thing is actually always to purge the new material from the screw and barrel. So we always recommend that. Sometimes when you go from light to dark, you can actually just change in the hopper. But typically, well, we would actually recommend to first clean the barrel, and it usually goes pretty fast, and start fresh there. So then we clean the machine, and cleaning is really sort of like looking at, for example, the interface between the sprue bushing. Sometimes a little bit of resin leaks out, the nozzle wasn't seated properly. So clean the machine nozzle on the hot sprue. This is, by the way, also a good time to double check if the orifices match. Then decrease the temperature on the barrel, because what we want to create is higher melt viscosity from the machine nozzle. We want to have that tougher material pushing out that lower viscosity material. And how do we achieve this? If we do it actually with the same resin, we increase the manifold and nozzle temperature. So that will actually lower the melt viscosity in the manifold, in the melt channels, and the nozzles. So the recommended increase is around 50 degrees Celsius above the operating temperature that's given by the hot runner supplier. And in the case of Husky, it's written on the side of the hot runner, actually. The next thing that you can do in addition to that, what really helps sort of scraping, even if it's not really a scraping action, but higher shear rates help changing colors faster. So what we actually recommend is to increase the injection pressure. You're not really concerned about making good parts, because the parts will be scrap anyway. So you shouldn't, at the same time, of course, exceed what your machine is capable. You don't want to cause damage to the mold or to machine. But in general, we recommend actually to increase the injection speed during the color change process. After the color change is complete, return the temperatures on the barrel and the hot runner system to your standard processing temperatures. Of course, don't forget to adjust the injection speed to your standard parameters so you make the same quality parts as before. And then start to produce parts with a new colored material. So that's basically it. But as you mentioned, or as the survey actually brought back, 56% of you don't actually have a written color change procedure, and I highly recommend that you change that. So in summary, I hope I was able actually to show that it's not just one element that influences color change, but a better understanding of the overall process hopefully actually helps a little bit to really optimize every aspect of your injection molding process. So it starts with pigment selection and processing do have a direct impact on color change time. If you know, for example, that you have that tough blue coming up in a given day or in a given week, you may want to consider a purge procedure. If you only have changing light to darker colors in a given day, you probably don't need to do that. But understanding the process is probably helpful. Color change time with hot runner is really dependent on three factors. The melt channel layout and sizes, they should be optimized for color change. Temperature uniformity, as I pointed out, has an effect in regards to how much boundary layer we create within the melt channels. What we especially have to look out for from a color change point of view is actually cold spots in the hot runner system. And then, of course, we want to eliminate any kind of hang-up spots within the system. What can also help color change is actually improved melt mixing in the machine and in the hot runner. So both of these actually can have a positive effect on a more effective color change. So in conclusion, if you want to master color change or improve on it, know your resin, the viscosity behavior, know your colorant. Feel free actually to get the colorant supplier involved. They actually have a lot of know-how and probably can help you with some tips and tricks too. And we're more than happy to actually sit together with the colorant supplier and us and then helping you from a procedural point of view. Select or configure equipment that's appropriate for fast color change, easy to clean, no hang-ups, an optimized hot runner design. Use mixing to disperse the color properly in the machine nozzle and in the hot runner, and apply a proven color change procedure. That concludes the webinar from a presentation point of view, and I would like to lead into the question and answer area. But just give me a second, and I start that. One of the questions is, would Husky recommend a solid color change or a liquid? From a hot runner point of view, we recommend a solid. What we have found, liquids are more difficult. Liquids have sometimes other advantages, but strictly from an injection molding process and hot runner point of view, what we have found, the solids are actually easier to change as an overall statement. There's a question in regards to temperature settings. During a color change, as I mentioned, actually we recommend to go higher. And the gentleman that asked is there a problem with thermal expansion? Could it actually cause, leakage, or could it cause damage to the components? Now, every hot runner is a little bit different. I recommend actually that you check with your hot runner supplier what the best way is and how far you can go. With the Husky system, we actually have, with our Ultra Seal technology, we can actually offer an operating window of plus minus 100 degrees Celsius without actually causing any damage or any leakage to the system. So the 50 degrees Celsius extra actually don't do any damage to a Husky system. So you're well within that range. Does the procedure in principle apply to valve gate systems as well as hot tip system? The principal procedure applies to both. So we don't really make a difference between a valve gated system and a hot tip system when it actually comes to color change. And by the way, that ultraflow tip is actually available for valve gate and for hot dip. There's a very specific question in regards to an 18 cavity mold with a 150 gram part, and the question is like, from an opaque point of view, is there any potential problems? And I think in principle I would say no. I don't know which kind of hot runner or what kind of system you use, but typically like the colorant itself, no matter if you make it opaque or if you make it with a solid color or a different material, usually does not have an impact in regards to part properties. I think what is more important is that you have an overall good process and actually do some testing with a specific resin afterwards. But from a foreseeing problems, I would say no, because oftentimes you have other additives in the parts too, and in a way a colorant is just one of the many additives that you can have. One of the questions is purging compounds again. We recommend UltraPurge. We have used that. Other people may recommend others. So I think the recommendation is check with your hot runner supplier what they recommend to make sure it doesn't do any damage to the systems, but typically it doesn't. One of the questions is actually if there's a difference in pressure drop with that mixing tip or the ultraflow and a conventional tip, and the answer is it depends on the resin. Like typically polyolefins we haven't really seen. We're now in our second generation with that mixing tip. We haven't seen a lot of pressure drop, but depending on the specific processing setup, the specific resin what you use, it's always a good thing to check back with Husky if we actually foresee any problems. But otherwise, principally no issue. Oh, there's a question that's a good one. In regards to purging the hot runner with the molding gates open, we do not recommend that for safety reasons. And also typically on most injection molding machines, when the gate and mold is open, you cannot use your full injection speed or your full injection pressure. And as I demonstrated during the presentation, shear rate is actually very important for fast color change. So because you're slowing actually down the system, you won't get that benefit of that increased shear rate. So we actually don't recommend it to do it this way. The best way is actually molding full parts at increased injection speed and pressure, not actually at decreased. There's a question in regards to like, what about if we run already at elevated temperatures and we're already seeing black specks, and then we want to do color change and increase the temperature even further? What would we recommend? In this case, I probably wouldn't recommend. Now, black specks actually have come from different sources. So I think one of the reasons that you may want to investigate first, why do you have black specks in the first place? Black specks can be created through hang-up spots in the system. They don't have to be there. I would recommend not to live necessarily with black specks, but actually rather try to figure out where they come from. But let's say that's the process that you run today, and you elevate temperatures further. You probably could do it for a short period of time, because most resins, even exposed for a short period of time to even higher temperatures, don't become carbon. That's what black specks basically are. That wouldn't happen in a short period. So if you just do it for quick color change, probably not that big of a problem. But generally speaking, if you're already running that high, it may not help that much at that point, because the percent increase, if you're running already 750 degrees Fahrenheit, another 50 degrees probably won't make a big difference in viscosity at that point in time. What an interesting question. How about big 10-kilogram parts? So I guess somebody is molding 10-kilogram parts in different colors. I would say, generally speaking, there is actually a rule. The larger the part, the more material you push through, the faster your color change. And the reason for that is because you have virtually no residence time in the hot runner, and while you're injecting these 10 kilograms of material, you're turning actually a lot of material over. So color change, in theory, should actually be faster. If you still have color change problems with a large part, I would actually check into issues other than, I would suspect, hang-up spots, maybe mismatches or something like this. You must have like really big areas within that melt channel system that probably doesn't clean out properly. But if you have smooth channels and everything well, a large part, in theory, changes color a lot faster versus, let's say, a 2-gram part or a 1-gram part.
Well, thank you, Martin, for such an excellent presentation. And most importantly, thank you all for attending today's webinar. We really appreciate your time and hope that you found it very valuable. Thank you again, and keep molding.